Everything around us, from the chair you're sitting on to the air you breathe, is made of tiny particles called atoms. Imagine a Lego set. Atoms are like the individual Lego bricks, and everything in the universe is built by putting these bricks together in countless combinations. Each atom is composed of even smaller particles: protons, neutrons, and electrons. Protons and neutrons huddled together in the atom's nucleus provide the atom's mass. Whizzing around the nucleus are the electrons, much lighter than their nuclear counterparts. Understanding atoms is like unlocking a secret code that governs the behavior of everything we see and touch. Among the subatomic particles, electrons are the social butterflies of the atomic world, constantly interacting with other atoms. The outermost electrons furthest from the nucleus's pull are the ones responsible for an atom's reactivity. These are the valence electrons, the extroverts of the atomic world. Atoms with a full outer shell of valence electrons, like the noble gases, are content and unreactive. On the other hand, atoms with incomplete outer shells are on the lookout for partners to share electrons, forming chemical bonds. Imagine an atom with a single valence electron. It's desperate to find a partner to share its lonely electron with. Now picture another atom with an almost full outer shell, just missing one electron. These two atoms are a match made in chemical heaven. They'll readily react, sharing that lone electron to achieve a stable, full outer shell. This sharing and swapping of valence electrons are the basis of chemical reactions, the driving force behind the creation of new molecules and compounds. Navigating the vast world of atoms and their properties might seem daunting, but thankfully chemists have a secret weapon: the periodic table. This ingenious arrangement of elements is like a map of the atomic world, organizing all known elements based on their atomic number. The periodic table is arranged in rows called periods and columns called groups. Elements in the same group share similar chemical properties because they have the same number of valence electrons. For instance, the alkali metals in group 1, like sodium and potassium, all have one valence electron, making them highly reactive. The periodic table also reveals the existence of isotopes, atoms of the same element that have the same number of protons but different numbers of neutrons. Atoms, like people, are rarely found alone in nature. They're social creatures, constantly forming bonds with other atoms to create larger structures called molecules and compounds. A molecule is a group of two or more atoms held together by chemical bonds. A compound is a molecule made up of atoms of at least two different elements. Imagine two hydrogen atoms, each with a single electron, yearning for a companion. They come together, sharing their electrons, and form a stable molecule of hydrogen gas. Similarly, a sodium atom readily donates its lone valence electron to a chlorine atom, forming sodium chloride, the familiar table salt. The formation of molecules and compounds creates the incredible diversity of matter that makes up our world. Atoms form bonds with each other in various ways, much like people hold hands in different ways depending on their relationship. The type of bond formed depends on the atoms involved and their electronegativity, which is their tendency to attract electrons. Covalent bonds are like a strong, intimate handshake between atoms. They occur when atoms share electrons equally, forming a stable and lasting connection. This type of bond is common in molecules like water and methane. Ionic bonds, on the other hand, are like a business deal where one atom donates an electron to another. This creates ions, atoms with a net electrical charge, which are then attracted to each other due to their opposite charges. Metallic bonds are like a giant group hug between metal atoms, explaining many of the properties of metals, such as their electrical conductivity and malleability. We experience matter in three primary states: solid, liquid, and gas. These states are not inherent properties of a substance, but rather a reflection of the energy and arrangement of its constituent atoms and molecules. Temperature, a measure of the average kinetic energy of these particles, plays a crucial role in determining the state of matter. In solids, atoms and molecules are tightly packed, like passengers on a crowded subway train. As temperature increases, so does the kinetic energy of the particles. They start to move around more, loosening the bonds that hold them together, and the solid begins to melt into a liquid. In liquids, particles have more freedom to move around, like dancers in a crowded room. As the temperature further increases, the particles gain even more energy and break free from their bonds, transitioning into a gas. Entropy, a measure of disorder or randomness, also plays a role in the states of matter. Solids have low entropy, liquids have higher entropy, and gases have the highest entropy.